Hello again. So for this video, we're going to consider a theoretical case, and then we're going to apply some decision making and some critical thinking regarding setting up a convolutional neural network for pose estimation. So for our theoretical case study, we'll do a low Earth orbit case. So to begin, we'll describe the case, and then we'll create some images for that case to train on. Then we'll discuss the creation of our convolutional neural network. And finally, we'll have some realistic considerations at the end to make. So to begin, let's discuss the case. So here, this image is of the RISE-SAT, which was a JAXA and Japanese University collaboration satellite. It was an Earth observation satellite launched in 2019. It's a microsatellite, and it was set up in a sun-synchronous orbit with a period of about 94 minutes. So an interesting question, though, is what happened to its launch vehicle? Because, of course, it had to get up there. So its launch vehicle was an Epsilon 4, and as we see on the right here, there's three stages. There's the first stage, which is comes back down to Earth. There's the third stage, which, of course, holds the payload. But there's also the second stage, which gets it up to its final orbit, but then what happens afterwards? And the truth is, it's still in orbit. So what does this orbit look like? Well, the orbit of this second stage will probably be pretty close to the orbit of its the target orbit of its payload. So here we can see a sun-synchronous orbit graphic on the right. We can see that the angle of incidence of the orbit is always the same with the sun, no matter where we are in our orbit of the sun. So what's our objective in this case? Well, our objective then is we want to create some realistic images of a rocket body in a sun-synchronous orbit for pose estimation. Okay, so let's move on to creating some images. So we created a model of a rocket in Blender, and it's fairly detailed, and we put in some thought and effort into the different surface materials. So we have glossy surface materials and matte surface materials. And Blender is actually an excellent resource because it's ray tracing software, and it's actually quite accurate from a physical standpoint. So we can set the intensity of the sun to the theoretical intensity of the sun in no atmosphere. So this is a relatively detailed object, and that's not necessary for if you want to do your own test study, but in this case, I think we have a very good target to work with. So now we've got to talk about the orbit. So since it's a sun-synchronous orbit, no matter what time of year, our angle with the sun will theoretically be the same, so that's nice. Here we show an orbit around the Earth, and then I've also indicated the hill axis, which is a local axis of an object in orbit with the x-axis always pointed up. So it's actually like this, I guess, as it orbits around the Earth. Additionally, I have two dotted lines there indicating possible vectors of where the sun might be at. And you can see that as the object orbits around the Earth, the hill frame changes. So in some sense, we have 2 degrees of freedom. One, in the hill frame, the object itself might be rotating or spinning, and as well, the hill frame is changing its orientation as it orbits around the Earth. So that's good. Now we have that simulated in MATLAB. And here are some images that we've rendered. The images from the left are at the equator, and the images from the right are at the North Pole. So you can see that where we are in our orbit, it very much influences the types of images that we might get. And I didn't say this, but theoretically, if we have an object that's spinning and there's a chaser object, that's where our camera is, and we're following the object in its orbit. So we're behind the object. As you can see, the images are quite different depending on where we are in the orbit. And the images on the left look like they might be very difficult. There's very limited information in some of those. All right, so now we can discuss a convolutional neural network to estimate the pose of those images. So this is a relatively simple case because it's a flat spin. So we don't need to get too fancy here. We can take a simple ResNet. And for those unfamiliar, a ResNet is a convolutional neural network that was developed for the COCO Image Recognition Challenge. I think that's 2015. in any case, we can see the different layers of the ResNet on the left and the right of the screen here. But I've circled the output layers here on the bottom right. These are the layers that we need to change for our own pose estimation work. Because this network was designed for image recognition, it's a very different type of problem than pose estimation. So one might ask, well, why don't we use a pose estimation network, one that was designed for pose estimation? And there aren't so many. The truth is there's a lot more researchers working on image classification and a lot of effort going into it and a lot of different data sets than there are for spacecraft pose estimation or even pose estimation in general. So to leverage all of that excellent research and all those wonderful architectures and progress, we can take a image classification network and then tweak it and retrain it and see if we can get good results that way. So again, on the bottom right, those are the layers we'll be changing. So we can zoom in on that. So on the top here, we have the original ResNet network. We have the full body on the left, and then we move into an average pool. So what is average pool? Well, if we have a 2D image, average pool takes a certain subset of that image, averages all the components, and returns a single value. So in that sense, for different regions, it can return a feature or that is perhaps the most important for that region. And then we go into a fully connected 1000. So that's because there's 1,000 different classes. And then finally, we go out to this fully connected softmax. So what is a softmax function? Well, a softmax function is an activation function which essentially squishes the output to between 0 and 1. So because we care only about classifying images in this case, we just want to know the probability that this image contains something or not. So for the softmax function, if we output if we're 70% sure or 80% sure or 90% sure that a cat is in the picture, that'll all asymptotically work out to be almost 1. So we're quite sure that a cat is in the picture. But if we're 30% sure a cat is in the picture, then it'll work out to be close to 0. So in this way, we kind of, it's a good activation function for our image identification. However, that is not a good activation function for a pose estimation model or a linear regression model, because we have a continuous set of values that we could possibly have and we're interested in. So let's pop down to our modified network. So again, we have the ResNet 18 body, and I've removed the average pool because we're not interested in which features from different regions might be affecting like the overall classification of an image. Instead, I want to take the different values from the different region to get a single number out. Essentially, like I want to know the pitch. So I don't want to know if a number of regions classify it as a furry animal and then it's a cat. We just want to get the pitch. So I want to essentially take all the information at the end and not have sort of a downsampled image. So then we're going to go to a fully connected 3 layer, and I'll explain why it's 3 in a minute. And then we're going to use a rectified linear unit 3. So what is a rectified linear unit? Well, essentially that outputs either, if it's a negative number, it outputs 0. And if it's a positive number, it doesn't change it. So it's just a 1-to-1. It's a linear output. And so, of course, that's good for our case. If we want to output a pitch of 20 degrees, it'll keep the number at 20 degrees. So you might ask, well, then why do we use a rectified linear unit at all? Why don't we just leave it as is? And that's a good question. The truth is, with these networks, is if you don't have activation functions, then it's a fully linear function the whole way through, from top to bottom. And so the network sort of degrades. It doesn't matter how many layers you have. If they're all linear, you just have a sort of very convoluted slope function. So we actually need to have some non-linear activation functions, such as a softmax or such as a rectified linear unit. We need to have them, at least a few, somewhere throughout the whole neural network. So you could argue, well, I don't think it should be at the end. And maybe that's the case. But in this case, I train the network to output a range from 0 to 360. So I think we'll find that it works out pretty well here. So again, why 3 numbers? We see the 3 numbers at the end I've chosen. We have the pitch, the angle we're trying to estimate. And then I also have a vert integer and a horizontal integer. So when I was training the network, I found the network didn't necessarily learn if I just asked for a single number. It never converged to a solution. But if I was also asking for a integer associated with vertical and horizontal, I found that the network converged much faster. So sometimes tweaking like this is necessary to help the network sort of find the solution or converge to something that's useful. So again, to simplify that, we're going to output a pitch. That's the number we want. But also, if it's pointed upwards anywhere in the top half, then it gives a vertical integer of 1. And if it's pointed down, it gives a -1. And horizontal, if it's pointed at the camera in any direction, it gives a 1. If it's pointed away from the camera, it gives a -1. So if we're pointed up and away from the camera, we'll have a positive vertical integer 1 and a negative horizontal integer -1. Okay, there's a lot to explain. Again, let's talk about how to train the network. So for our image classification, typically we use a cross entropy loss, which is the function here. So y is the true answer, and then y hat is the estimation. So if the image is a cat, and cat is number 1, or I equals 1, then y will be a 1, and our estimate may be 0.8, and then the log of 0.8 minus, sorry, I guess I'm just explaining the math here, but essentially that is not appropriate for what we're trying to do here, which is another linear regression problem. So instead we move over to a mean squared error loss, which is our estimate is y hat, and the ground truth is y. So if we subtract the true pitch of, say, 20 degrees from our estimate of 18 degrees, how much closer can we get? We're trying to minimize the mean squared error loss. So these are the types of considerations we need to make when we're transitioning a image classification network into a linear regression network. Okay.